Hey everyone, how are you? In this video, I will do a detailed feature engineering project based on live stock market dataset, that is OHLC data, open, high, low, close, and then build a LGBM model on that and finally come out with the most important features as predicted by the model. And for the dataset, I will use this pretty famous Kaggle competition that got over a few months back, which is JPX Tokyo Stock Exchange prediction. And there was indeed a $63,000 award prize for this competition to come out with the best prediction. So this competition will involve building a portfolio from the stocks eligible for prediction. Specifically, each participant ranks the stocks from highest to lowest expected returns and is evaluated on the difference in returns between the top and bottom 200 stocks. And you will have access to financial data from Japanese stock market here, such as stock information and historical stock prices. And if you go to the data tab of this competition, you will see all the required data. So here are the most important data that you will need for this exercise, and the one that will be using the stock prices CSV, this file, and this is around 217 MB. And the data set is pretty simple, the one that you would expect for any stock market or securities market related data. That is, we have all this OHLC, open, high, low, close, and then volume, adjustment factor, etc. So adjustment factor, we'll discuss about this particular column later. And also we have the securities code, which is the unique identifier of the relevant securities. And a few of the description of this dataset is the stock prices.csv. The core file of interest includes daily closing prices of each stock and target columns. Then this one also will be using stock list.csv. This is a mapping between the securities code and company names, plus general information about which industry the company is in. And I'm looking at the stock list.csv, where we can see the securities code and the corresponding name of the company and also the sector name. So we have many columns for the relevant sector names. So this will be useful for drawing some of the plots that we'll be doing based on the return on overall sector, like which sector gave the most return and so on, things like this. And once again, the goal of this competition is that this competition will compare your models against real future returns after the training phase is complete. The competition will involve building portfolios from the stocks eligible for predictions, around 2000 stocks. Specifically, each participant ranks the stocks from highest to lowest expected returns and is evaluated on the difference in returns between the top and bottom 200 stocks. And about the evaluation of your prediction, this is what they say, that submissions are evaluated on Sharpe ratio of the daily spread returns. You will need to rank each stock active on a given day. The returns for a single day treat the 200 highest ranked stocks as purchased and the lowest ranked 200 stocks as shorted. The stocks are then weighted based on their ranks, and the total returns for the portfolio are calculated assuming the stocks were purchased the next day and sold the day after. So we will build these Sharpe ratio method to evaluate it. But one quick point to note here, that I no more can send my prediction to the competition for evaluation purpose, because the evaluation was based on an API from the competition host in Kaggle, and that API closed after the competition was finalized 7 months back. But what we will do instead is we will build our own Sharpe ratio method and build the cross validation within our dataset, that is dividing the data into various validation folds, and then calculate the evaluation score based on that. Alright, I'm in my VS Code and I have actually downloaded the whole data in my local machine, so I'll be referring from there. But in case you really don't have to download, you can run the entire code within Kaggle kernel. So initially I'm just defining some of the const here. So the first two lines are just defining some of the global attributes of the Plotly library that I'll be using throughout this exercise. And then I'm just reading the stock prices.csv file and printing the train.describe. So train is my main stock prices.csv, and that's description I'm seeing right here. So we have open, high, low, close, volume, adjusted factor, expected dividend, and target. And what we are seeing here is some of the statistics of the entire data set that is going by each column. And the statistics are all these mean, then mean, max, standard deviation, all these things. And then just read the data, the trend.head. It's just what we saw in the Kaggle's official page. All right, now I just want to draw a histogram of the target column. And once I complete the histogram, this is a plot we get. This is plotting the distribution of the target mean. And for the entire dataset, we also have these extra statistics. We have mean value, max value, skewness, and kurtosis. So after this, I also want to print or plot the target standard deviation distribution. So this is the code right here. It's just exactly the same code. Only thing I'm changing is sns.histplot. Data remains the same. Only thing I'm changing here is instead of mean, I'm using the STD. So that's my plot for target STD distribution. And next, I'm going to plot the yearly average stock returns by various sectors. And for that, I need the stock list CSV file. And so here I'm reading that, just the head of that, first two rows. So we can see that there are various section head, column head, I mean. So one, for example, is 17 sector code, then 17 sector name. Then we also have things like 33 sector code, 33 sector name. So they have in the competition host, the official page has actually given some description of this. Let's go there and see. So in the official page, there is a folder data specification right here. And that's where you will find all the definition of the various columns of all these individual CSV files that we have been given. So the one that we are interested for now is this one, stock list spec, because that's what defines all the specification of the stock list.csv. Okay, so here if I go to these two things, that is a 33 sector name and 17 sector name. This is the two sector names that we have been given, and I'm interested that which one I should use. So what they are saying, the 17 sector name, this is the sector name of this is the sector names, and for the reference we have been given an official PDF document coming straight from Japanese Stock Exchange. So let's open that PDF file. So this is the PDF file. And looks like this is the one that we are going to use for our sector name, because all these individual numbers, they are actually represent various sectors. So they say 17 series indices consist of indices are created by dividing the topics, the constituents of topics into the following 17 categories. English is not very perfect here because it's coming from Japan. So don't worry about this. It still makes sense that these are actually various topic sector indices, all these numbers. So anyway, the point is that we are going to use the 17 sector name, this column of the stock list.csv file for our sector names. So what I did here, this first two method is just kind of pre-processing. So the first method, it just takes a original stock list CSV file and does some pre-processing and creates these two clean column names, sector name and name. Then in this method, I'm just merging the output from the previous method with my train CSV file and creating this train DF. And I'm merging because I need a single data frame which will have both these column names, that is securities code, name and sector name, and also the entire train DF where I will have the actual return, that is the target values from my train DF. And remember, train DF looks like this. So this has all the main price data of the securities and also the target, this value, the most important for this particular cell here, because this one represent the year to year the time to time return of the corresponding security. All right, now this get yearly average return, this is like the main function in this particular section right here, because this creates the year wise return from the previous two data frame. So this function creates the dictionary first, this years dictionary, where each key is a unique year in the train DF data frame and the corresponding value is an empty data frame. So the years are sorted in descending order because of this particular slice notation here, which is reversing the list. And then once I have this dictionary, enter a loop over the keys of the years dictionary, that is over each unique year, and then apply these two things, these two operations to each year. So first I filter the data to keep only the rows where the years is the current year, that is I'm passing this particular condition here, train df dot year equal to key, and the key here represent each unique year over here. And then this line, this entire line, what it does is that it groups the filtered data frame by the sector with this group by pandas operation, and calculates the mean of the target column, which represent the return of the stocks, and then multiplies it by 100 to convert it to a percentage number, and renames it as average return followed by the corresponding year. The result is a series that is then stored in the years dictionary under the key of the current year, and then this concatenation operation will concatenate the series in the years dictionary into a single data frame df, where each column represents the average return for a year and each row represent a sector. But to complete the plotting methods, I need two further methods. The first one is add bar traces. So this function is just a single line actually. What I'm doing in this function is just doing this fig.add traces and then passing the various configuration within the add trace method. So this function is used to add to the figure a bar graph that represents the average return of the stock in each sector for a specific year. The bars are separated by whether the return is positive or negative, indicated or controlled by these mask attribute right here. If the return is positive, the bar is green. If it is negative, the bar will be red. But green and red, that control will do in the next method. And another method that we will need to complete the plot is this one, create yearly average return plot. It takes a data frame and a template. So let's go over quickly what this is doing. So it will enumerate over df.columns, and each of the column within the df.column represent a single unique year. And so the important point here is this particular condition mask. While I'm controlling for the mask, this actually controls a positive and negative return in my data set. So basically this line mask equal to x less or equal to 0 is used to create a Boolean mask for the X series, which contains the average returns for a given year. This mask has true value for elements in X that are less than or equal to 0 and false values for elements greater than 0. And the purpose of creating this mask is to separate the bars in the plot into two categories based on their average returns. So bars with negative or zero return will be red, and which will be identified by the mask, and bars with positive returns will be green, which are identified using the inverse of the mask. So you can see this symbol right here, which represents the inverse of mask. And once my mask has been controlled properly, then I'm just updating the x-axis, so with this line, and for the data I'm passing x.mean and x.max. Actually, this part, that is this range parameter, sets the range of the x-axis for the current subplot. It is said to be slightly wider than the range of the data by subtracting 0.15 from the mean and adding 0.15 to the max. And also part of these attribute is these two things, row equal to 1 and col equal to I plus 1. So this specifies the position of the subplot that is being updated. The plot is a grid of subplots, and this specifies which subplots x-axis properties are being updated. Row equal to 1 specifies the first row, and col equal to I plus 1. This specifies a column based on the loop index I, which is this one. And after I execute all these methods and define the relevant variables, I get finally as this data frame yearly average return DF, which is what we will use to plot our next plotting. And this data frame is just as we are expecting. Each of the columns is an unique year, and each of the rows represent one sector. And now finally for the plotting, I'll just execute this command or this code. And that's it. I get my beautiful plot where we have individual years right here, 2021, 20, 2019. And each column, each vertical column represent the returns of the various sectors. So we can see that in 2021, nearly all industries saw a positive return on average, with the highest being energy resource industry at about 0.13% overall, while in 2018, this year, nearly all of them are red. That is, mostly all created negative returns. Alright, next plot I want to do is distribution of the target variable by sector, and it will be a box plot. So we got this beautiful plot, and looking at the plot, we can see that most of the sectors creates a return between -4% and +4%, but there are quite a few outliers. For example, this return right here for commercial and wholesale trade is at 62%. Similarly, we have on the negative side this one, almost -31% for IT and service and others. So this is a box plot, and basically the boxes here represent the daily spread between the open and close prices, and the lines represent the spread between the low and high prices. The color of the boxes indicate whether the close price was greater or lower than the open price, with green indicating a higher closing price and on that day, and the red indicating a lower closing price. And coming back to the code here, just a quick explanation on this method, create color palette. So this function generates a color palette with a specified number of distinct colors. These colors are then used to differentiate different sectors when visualizing the target distribution that we just saw. So we are using here np.linespace. So this is a linear spacing function which generates evenly spaced values over a specified range. Here it is creating num colors number of values between 0 and 360. These values will be used as the hue, that is H, for the HSL color space. And that's what I'm using here, HSL. So this stands for hue, saturation and lightness color model. It's a way to represent colors. Hue is a degree on the color wheel from 0 to 360. 0 is red, 120 is green, 240 is blue. And saturation represented by this 50%, and the lightness is represented by this 50%. So the whole expression, this whole thing, this is creating a string representation of a color in the HSL color space. For each value in H generated by np.linspace, it is creating a color with that hue and a saturation and lightness of 50%. The resulting list of colors will be evenly distributed around the color wheel, providing a variety of colors for the plot that we generated right here. And next I'm going to do the coding for this plot, which will show the stocks with highest and lowest return by sector. For example, this one is showing all the sectors together. I can also do by individual sector, food, for example, energy and resources, things like this. So let's code it up. After I ran this long method, this is the beautiful plot I got. And you can see that with right now all the sectors are chosen by selecting all here. And so I have the 7 highest performer and 7 lowest performer, that is 7 largest and 7 smallest. And we can choose between different sector, just like this. For example, food sector, I have the 7 top performers and 7 bottom performers. So let's quickly go through what we just did over here. So first, in the get stock function, this is to identify the best and the worst performing stocks, both overall and within each sector. And we do that by first we chose the top 7 performer among all the stocks. That is when all is selected, that is all sectors, we take in smallest and in largest, and then do a concatenation of those 2 data frame. So that is the first situation, and then we actually loop through each of the unique sector name, and then within each sector we group by the name and take the smallest 7 and largest 7. And the reason for this is what we just saw in the plot, that we want to select all sector like this, and also we want to select each individual sector. So that's the reason we did that there. All right, moving on the next few methods. So the create bar trace and create buttons are just 2 small helper method. They are not doing pretty much anything. You can just go through them. For example, create bar is just a single line. It just implement a geo.bar and then passes all the configurations. And similarly, create buttons, its only job is to return this dictionary, which will have a label, which are the sector, and another important thing is visibility. And then important method here is this one, create plot method. And within this method, so just one point here, that is this create plot method will work with this stock data frame. This is the concatenated data frame that we got after executing this get stock method. And get stock method will concatenate the result of this get stock method is what you can see here. That is, this is the stock, this is a return, that is a return output from the get stock method. And what we see, this data frame is just a simplified version of our original trend DF data frame. So we have the name of the company's corresponding return and the sector, and this is what we'll work with within create plot method. So initially I am just looping through the stock.sector.unique values. Again, the sector is this, so we will have unique values from individual sector, and then my X value is the name of the company and the Y value is the corresponding return, that is average return, percentage return, that is. Now, important point in this method is these 2 lines mainly, this mask equal to Y greater than 0, and then these 2 lines where I'm setting the visibility. So mask we are using here, we can see that when we are actually creating the bar trace, we provide X mask, Y mask, and then the opposite of X mask and Y mask, and that is with the reverse values of mask. So let's understand what this mask is all about. Now coming to the mask variables interpretation. So this line is creating a Boolean mask for the return values of the stocks, because Y represent your return values. This mask is a panda series of the same length as Y, which is a series of return values for a particular sector or particular stock here. But instead of numerical values, this mask contains a Boolean value, that is true or false, for each item in the series. And in this case, mask will be true for every stock that had a positive average return and false for every stock that had a negative or 0 average return. And why is this useful? The reason is that the primary reason here, that it allows for the separation of the stocks with positive and negative returns. This is used in the next line right here, where I'm selecting X mask and then the opposite of S mask. So basically these 2 lines are just adding a trace to the plot for each group of stock. And for all the positive return stock, I'm showing them as green, and all the negative return stock, I'm showing them as red. We can see that right here when we are actually seeing the plot. And that's being controlled with this mask variable here. All right, and next, coming to these visibility parameter, these two lines are extremely important because this is basically controlling the visibility of which plot we'll see. For example, right now we are seeing the plots of the all sectors, that is all individual sectors are hidden. And then when we are choosing any particular sector, for example foods here, now except for foods everything else is hidden, and we are only, the foods is the only visible thing, and that's the thing that is getting controlled with this visibility variable here. So as to the explanation, these are part of the process of creating interactive buttons for the plot, which allow the user to switch between visualizing the stocks of different sectors. This is made possible through the use of update menus attribute of the Plotly figure layout. So the first line, that is this one here, this is creating a list of Boolean values all set to false that will represent the visibility status of each trace in the figure, and we are multiplying it by 2. Why? Because each sector's data is represented by 2 traces, one for stocks with positive return and one for stocks with negative returns, and there are total this many unique sectors. So the total number of traces that will be required is 2 multiplied by the length of the unique sectors, and that's the reason we are doing this expression. Now the second line, this one, this second line is updating 2 specific values in the visibility list, setting them to true. The indices being updated are I multiplied by 2 and then I times 2 plus 1, where I is the current index in the loop over sectors. This means that for each sector, 2 corresponding traces are set to be visible. And the logic behind this is that a user selects a sector using the drop-down menu. Only the traces corresponding to that sector should be visible in that case, while all other traces should be hidden. This is achieved by creating a separate visibility list for each button where all values are false except for those corresponding to the traces of the sector associated with the current selection of the user. And in the final figure, each button in the drop-down menu is associated with a unique visibility list. When a button is clicked, the visibility attribute of all traces is updated according to the associated visibility list, effectively showing only the traces associated with that button and hiding all other. And next idea that I'm going to do is this plot where we will show the most correlated stock with the target variable. We run this create most correlated plot. This is the result we get, and this just shows the 10 top correlated stocks, and the correlation is with the target variable. Now, let's quickly understand what we did in this code. The first method, this get most correlated stock, this is like the most important method in this whole exercise. I mean, in this part of the exercise. And within this method, the really key line is this one. And let's look at these step by step, each part of this line, because this line does actually the whole job of getting the most correlated stocks and also restructure the data frame in a proper fashion. So this part, target, close and correlation, this operation calculates the correlation between the target and the close columns for each grouped data frame, that is for each stock, because we are grouping by securities code which represent one single stock. And this correlation method, this returns a correlation matrix, which is a square matrix that contains the correlation coefficients between each pair of variables. Since we only have two variables, that is target and close, our correlation matrix will be a 2 by 2 matrix for each group. Now, let's look at this part. We are doing an unstack here, and the key question is why exactly we are using that and what exactly it does. So, unstack is a method. This operation actually reshapes the resulting data frame. It pivots a level of the column labels and turns them into row indices, producing a new unstacked data frame. What do I mean by that? So let's look at the output of this. So this is the output before applying the unstack, and we can see that when you apply the correlation method after grouping by securities code in the data frame, you get a multi-index data frame as a result. The multi-index data frame has two levels of row indices, the securities code and the variables target and close. The columns also have two levels, which are again target and close. So the main point that confusing about this data frame is that we have two columns, target and close, and also a multi-level at the row level, target and close. So here you can see that across the diagonal, that is these one values, which represent the correlation of target with itself and close with itself, which are both redundant. And so the another redundant part is this diagonal, that is the correlation between target with close and close with target. They are both the same, right? So here the thing that I want to achieve is that to have a series or data frame where each securities code is associated with the correlation between its target and close values. To achieve this, the unstack method is used to pivot one of the levels of the column levels, which are also target and close, and make them part of the index. And so on this data frame, when I apply this unstack method, I get this result. And we can see that here I have target close. Now I need these values. I want to get rid of all the redundant values. And for that, I am applying these integer location, slice and 1. What this does is, it selects the second column of this data frame, which is a correlation of close with target. So basically the use of unstack here is a way to restructure the result of the correlation method so that it's easier to select the desired correlation and get rid of all the redundant correlation values. And the rest of the method in this part, that is create color palette, create most correlated stock plot, add bar trace, they are just kind of helper methods to create the plots. For example, create color palettes is just creating a number of color palettes based on the number of stocks that we have, because we are selecting the length of the stocks. And create most correlated stock plot is just ultimately creating this figure with update layout and passing all the configuration to actually create the plot and show it. And add bar trace, this is nothing, this is just adding a trace with a bar plot. Alright, with that, now next plot that I'm going to do is heat map with stock correlation between the sectors. Let's code it up. correlation plot is now plotted. Now quickly understand how this code worked here. So the first method, create pivot table. This just creates a single pivot table from the given data frame, and our data frame is 20F. So basically what it's happening is that I have printed the actual result. So here, this is exactly the code that I have taken from this one here to see the effect of the pivot table. So the pivot table function takes in a data frame and the parameters detailing the shape you want the data to take. Then it outputs a summarized data in the form of a pivot table. Here I'm passing the index equal to date. This sets the date as the index of the pivot table. This means that each row in the output table will correspond to a unique date found in the date column of the input data frame. And columns, I'm passing a sector name. So this sets a sector name as the columns of the pivot table. This means that each column in the output table, that is, this is the output table, will correspond to a unique sector name found in the sector name column of the input data frame. And values I'm passing as close. This specifies that the value in the pivot table should be taken from the close column of the input data frame. If there are multiple close columns for the same date and sector, they will be aggregated by default using a mean value. So the result of the pivot table function is a new data frame with each row corresponding or representing a unique date and each column representing a unique sector. The intersection of the row and the column will contain the corresponding close value for that date and sector. And then I am doing this function, calculate correlation matrix. Here the main thing that we are passing a correlation numpy array, and then it is applying the np.triu, this method on that correlation after creating np_like. So let's understand how this works. So first, this expression np.like, and the entire expression here creates a boolean, creates a new array of the same shape as the input array CORR, but filled with boolean true values. And then the all-important np.triu, this method. So this method returns the upper triangle of an array. In this case, it takes a boolean array created in the previous step here. And then the output is a new boolean array where the elements below the main diagonal are replaced with false. And so the purpose of creating this upper triangle boolean mask is to remove the redundant lower triangular part of the correlation matrix, as well as to remove the diagonal, since the correlation of a variable with itself, which is represented in the diagonal, is always 1. So we want to remove that. And this is done to make the heat map plot more concise and easier to read by showing only the unique correlation between different sectors. And lastly, this part np.where. So after creating the mask here, it is used in this function to set the lower triangular part of the correlation matrix to the value of 100. This is done to differentiate these values from the actual correlation coefficients, which will always be between -1 and 1. And later in the extract correlation values function, we will remove these 100 values and only keep the unique correlation coefficients in the final heat map plot. So that's exactly what we are doing in the next method, extract correlation values. That is, we are excluding the 100 numbers from the correlation. But first, while we are looping through cmarks.toList, we are excluding the first one, that is with the slice notation. So we are slicing here to exclude the first row, which corresponds to the row with the value of 100 that we previously set in the calculate correlation mask function. By doing this, we ignored the first row because it contains no meaningful correlation data. The remaining rows represent the unique correlation between different sectors. And another important thing to note here is this expression here. So here we are reversing these COR variable, which will have all the individual numbers. And the reversal is needed because when we create the COR list by iterating through the CMask, we append rows in the original order, and the heatmap plot displays them from top to bottom. By reversing the list, we make sure that the sectors are displayed in the correct order in the heatmap plot. Alright, next I'm going to do is generating adjusted close price to account for any stock splits or reverse splits. And this method that I'm going to write now, it's pretty much taken from this particular link, which is one of the code that was submitted in the Kaggle competition. And I have only made some syntactical changes, and they are pretty much cosmetic changes. So the purpose here is that we will generate adjusted close using adjustment factor value. This adjustment factor value was part of the original data frame that was submitted, that was given as part of the input training data frame. And this should reduce the historical price gap caused by split and reverse split, which is what happens with the stock price. Using the stock's adjusted close price, I will create a set of new features, including the stock price moving average, exponential moving average, return, and volatility, each over a period of 5, 10, 20, 30, and 50 days. So they will be part of my feature engineering. But first, let's write the code for the adjusted close price. get all these features right here. So these are my all the features that I'll be using in my modeling next, and we can see that these are the new features that we just built: Bollinger lower, Bollinger upper, exponential moving average 20-day, volatility 200-day, etc. So all these we will be using in the model. And the next is price prediction. But before the price prediction, we have to build the custom function for calculating the evaluation metrics. Now, submission for this competition are evaluated based on the Sharpe ratio of the daily spread of returns. You can, of course, check the official pages guidelines on this. So, for each forecast day, all active stocks will be ranked in order of their predicted returns. The returns for a single day treat the 200 highest ranked stocks as purchased and the lowest ranked 200 stocks as shorted. So we have to rank both for our buy position and short position. That is, the top 200 will be the buy position ranking, and the lowest 200 stocks will be the shorted position ranking. And the stocks are then weighted based on their ranks, and the total returns for the portfolio are calculated assuming the stocks were purchased the next day and sold the day after that. That we just saw, calculate the Sharpe ratio. Now let's quickly explain the most important parts of this function. So here in this line, weights equal to np.line space, what it's doing. So this line is creating a linearly spaced array of weights using the numpy.linspace function. This array will be used to weight the returns of the equities in the portfolio, which is what we are doing here, that is multiplying each value with these weights, but these weights are calculated here in this line. So the weight starts from top ranked ratio and end at 1. This means that the most highly ranked equities, that is rank 0, will be given a weight of top ranked weight ratio, while the least highly ranked equity, that is rank portfolio size -1, will be given a weight of 1. All other equities will be assigned weights linearly interpolated between these two values. And the length of the array is equal to the portfolio size, which represent the number of equities to buy or sell. In this case, that's 200 as per the requirement of the competition, that we are calculating the top 200 to purchase and top 200 to sell. And then the next important line is here, calculating actually the weighted stocks to purchase. So this one, the first one is this part, that is we are using the slice notation here, and this slices the portfolio size entries, which are 200 from the target column in the data frame, which has been sorted by rank. The target column represents the expected return of each equity, as you already know. And then this sums up these weighted returns to calculate the total weighted return from the purchased equities in the portfolio. And finally, we are dividing by weights.sum. This calculates the mean of the portfolio. Oops, sorry, I just found out this little error I did here. The division should be by the mean of the weight. So that would be mean, and here as well it would be mean, right? So what we are doing here is calculating the mean of the weights, dividing the sum of the weighted returns by the mean of the weights normalizes the result, giving an average return that takes into account the relative importance of each equity as determined by its weights. So the exact same thing we are doing for the sorted part of the portfolio as well. Only difference here is that the sorted data frame here is by ascending equal to false. That is, we want the worst performing stock or equity at the very top, and taking the worst 200 stock to be sorted, and deducting the purchase return by from the sorted return. This will give us actual return. It may be negative if the sorted return is more than purchase. And then the next two lines are just calculating the formula of Sharpe ratio. That is, we are taking the daily spread returns from by applying these method calculate spread returns per day to each equity in the portfolio, which are by date. And then the Sharpe ratio is just the spread returns dot mean divided by spread returns dot standard deviation. That's the definition of Sharpe ratio. Okay, now that our evaluation metric is ready, we are ready to train the LGBM model. So let's write the code for that. Feature importance head, and this is the most important features. And next I want to plot those most important features, but before that just calculate a few things like an average column by taking the mean of the feature importance data frame across axis 1, then sort values by the average column with ascending equal to true, and then define a palette for my SNS.color palette. And now let's write a method to plot the feature importance. in this code, the training code I'm talking about. So first thing is that why do I need these time series split for time series project cross validation? What's the specialty of this class that I'm using here? Well, time series data has an inherent temporal ordering which makes it fundamentally different from cross-sectional data where observations are typically assumed to be independent. This temporal ordering of a time series can lead to what's known as autocorrelation, where observations that are close together in time tend to be more similar than observations that are far apart. So when validating a time series model, it's crucial that the model is not allowed to peek into the future. That is, a model should never be trained on data from the future relative to the data it is being used to predict. If this happens, the model's performance will likely be overly optimistic, as it is making use of information that would not actually be available at the time of prediction. And traditional k-fold cross-validation does not respect the temporal ordering of observations. For instance, in a 5-fold cross-validation with using a traditional method, the model might be trained on fold 1, 2, 3, and 5 and then tested on fold 4. This would be a problem for time series model, as it would be using data from the future, that is fold 5, to make prediction about the past, that is fold 4. And hence this solution comes to our rescue. This time series split from sklearn.model selection is a cross-validation scheme that respects the temporal ordering of data. Alright, that was the training part. And then in the next method that we just wrote, create feature importance plot, here this method is just for plotting the most important features, and the output when we run this method is this. So these just shows the overall, the top important features coming from our LGBM model. Alright, with that, this exercise pretty much ends, but I just want to note as well that in case you wanted to submit to the Kaggle competition, you have to add some more code. But the important point is that you can no more submit to Kaggle right now, because the competition has been finalized and the awards have been given. And with that, the API which was required for submission to the Kaggle competition is no more active. That API has been closed. So we cannot submit anymore, but anyway, I'm still adding these few lines of code just in case to show you that how it could be submitted to the Kaggle competition for evaluation and inferencing with their own test data set, which was coming from the API that is no more active right now. And in this code, what I'm doing is I'm taking this call fin from the important features that we earlier derived. With that, I'm also extending the call fin with open, high, and low, and then creating my X train and Y train from this call fin, and then running my LGBM regressor with the parameters that we have earlier defined, and fitting my X train and Y train. So this will give you the train model GBM, and on this model, train model, you have to submit to Kaggle competition for inferencing on their test data set. Alright, that pretty much wraps up this video. Do stay tuned, because I am planning to do quite a few interesting projects over the coming weeks and months. So thank you very much for watching, and see you in the next one.